Okay, so numerical differentiation methods compute approximations to the derivative of a function from known values of the function. So numerical differentiation methods, what they do, they actually compute approximations for the derivative or to derivative of a function from known values or known data. So if we provide a known data of a function and we construct a computation which will be approximated to derivative. So approximating derivative is very important in constructing finite difference methods for solving differential equations. Because these derivatives are involved in differential equations, so that is why approximating derivatives is very important in constructing methods to approximate derivatives is also important to deal with the differential equations. So approximation of the first derivative is simple approximation of the first derivative can be written as, so by definition even we can write f of x plus h minus f of x over h for a small positive number h. So this is the definition of first derivative. So actually f of x plus h minus f of x is the difference of points on y-axis, okay, are in the range, and x plus h are 2 points in the domain. So if we subtract 2 points of the range, that is f of x plus h minus f of x, okay, and we divide it with the difference between the points of domain, we will have this first derivative. And this first derivative can be written approximately equal to the f prime of x because the first derivative is denoted with f prime of x. In fact, derivative of a function at point x naught is given by, so if we replace this x with x naught, we have actually fixed the point x naught, and then a small increment in x naught is x naught plus h, and the point of range for x naught is f of x naught, and the point of range for x naught plus h is f of x naught plus h. And what's the difference between these 2 points in the domain is x naught plus h minus x naught, and it will gives h. So we can apply limit here, that is h is a very small positive number that can be approached to 0 or very close to 0, which yields an obvious way to generate an approximation to f prime of x by simply computing f of x naught plus h minus f of x naught over h. Okay, so a simple approximation of the first derivative can be written as f prime of x approximately equal to f of x plus h minus f of x over h. In fact, derivative of a function f of x at point x naught is given by limit h approaches to 0, f of x naught plus h minus f of x naught over h. So limit h approaches to 0 mean h is very small positive number. So this approximation that this derivative yields an obvious way to generate an approximation to f prime of x by simply computing f of x naught plus h minus f of x naught over h. Okay. So for small values of h greater than 0, it means h is a positive number. For linear functions, so if we have a function linear, the formula 12.1 is actually an exact expression for the derivative. But for almost all other functions, it is not the exact approximation. So if we have a linear function, or if the given function is linear, so this formula, computing derivative, so is actually an exact expression for the derivative. But if the function is not linear and for all other function, it is not the exact approximation. Okay. So in order to deal with this issue, we need to compute approximation errors. So Taylor expansion of f of x plus h about x can be written as f of x plus h is equal to f of x plus h f prime of x plus h square over 2 f double prime of xi. So xi belong to the interval x and x plus h. So Taylor expansion of f of x plus h about x can be written as f of x plus h is equal to f of x plus hf prime of x plus h square over 2 f double prime of xi. Xi belong to x, x plus h. So here, so we can say that to introduce an error term, there exists a number in between the values x and x plus h, and such that if we take a double derivative of the function, okay, and put this value of xi or the point, or we calculate the double derivative at the point xi which belongs to the interval and multiply h square with 2, so that is the actually error term. For such an expression, such an expansion to be valid, we must assume that f of x has two continuous derivatives. So that we have to suppose that the first derivative of the function exists and also the second derivative of the function exists. So that is why we can say we must assume that f of x has two continuous derivatives. Taylor expansion 12.4 can be written as, so Taylor expansion in the previous, this one 12.3 can be written as f of x plus h minus f of x. So this one, okay, so over h minus h by 2 f double prime of xi, and xi belong to the interval x and x plus h. Since this approximation of the derivative at x is based on the values of the function at x and x plus h, therefore the approximation is called forward differencing or one-sided differencing. Similarly, approximation of the derivative at x that is based on the values of the function at x minus h and x, that is f prime of x is equal to f of x minus f of x minus h over h, is called backward differencing. Okay. So since, yeah, we can repeat from this one. So since this approximation of the derivative at x is based on the values of the function at x and x plus h, therefore the approximation is called forward differencing or one-sided differencing. Similarly, approximation of the derivative at x that is based on the values of the function at x minus h and x, that is f of x minus f of x minus h, is called backward differencing. Second term on the right hand side of the equation 12.4, this one, so this term is called actually the error term. Okay, since the approximation can be thought of as being obtained by truncating this term from the exact formula, this error is called the truncation error. Okay, so since the approximation can be thought of as being obtained by truncating this term from the exact value formula. This error is called the truncation error. Small parameter h denotes the distance between the 2 points x and x plus h, or you can say the difference between x plus h and x is denoted with the small positive number h. As this distance tends to 0, h approaches to 0, the 2 points approach each other and we expect the approximation to improve. So if we reduce this h up to 0, so the improvements is getting better and better. The 2 points approach each other and we expect the approximation to improve. This is indeed the case if the truncation error goes to 0, which in turn is the case if f double derivative xi is well defined in the interval x plus h. The speed in which the error goes to 0 as h approaches to 0 is called the rate of convergence. So what is the rate of convergence? So rate of convergence is the speed in which the error goes to 0 as h approaches to 0. So if we reduce the error, so it depends on the speed of reduction of error when h approaches to 0. So this is called actually rate of convergence. When the truncation error is of the order O of h, that is a linear because h power is linear, we say that the method is a first order method. So we refer to a method as a pth order method if the truncation error is of the order of big O h power p. So this is the big O notation which is used to write the complexity of the algorithm, that the algorithm is how much is efficient or slow. So we denote it with big O. So big O of h mean first order method, it means so it's converge linearly, and if the if the polynomial of convergence has a degree p, so we can write it big O of h power p. It is possible to write more accurate formulas than 12.4 for the first derivative. For example, a more accurate approximation for the first derivative that is based on the values of the function at the points f of x minus h and f of x plus h is the center difference formula. So center difference formula can be written as f of x plus h minus f of x minus h over 2 into h. So to verify that this is more accurate formula, we can proceed as. So let's take the Taylor series expansion of f of x plus h can be written as f of x plus h f prime of x plus h square over 2 factorial f double prime of x plus h cube over 3 factorial f cube triple prime xi1. So then f of x minus h is equal to f of x minus h f prime of x plus h square over 2 factorial f double prime of x minus h cube over 3 factorial f 3 times derivative of xi2. So xi1 belong to the interval x plus h and xi2 belong to the interval x minus hx. And then we have this first derivative as f of x plus h minus f of x minus h over 2h and minus h square over 12. Okay, f, no, so triple prime of xi1 and minus f triple prime of xi2. If the third order derivative is a continuous function in the interval x minus h x plus h, then the intermediate value theorem implies that there exists a point xi belong to x minus h, x plus h, such that f double prime of xi is equal to 1 by 2 f triple prime xi1 plus f triple prime of xi2. Hence, f prime of x is equal to f of x plus h minus f of x minus h over 2h minus h square over 6 f triple prime of xi1 xi. In a similar way, we can approximate the values of higher order derivatives. For example, it is easy to verify that the following is a second order approximation of the second derivative. So what is the second derivative? Can be written as f double prime of x approximately equal to f of x plus h minus 2 f of x plus f of x minus h over h square. To verify, we expand the terms as f of x plus minus h is equal to f of x plus minus hf prime of x plus h square over 2 factorial f double prime of x plus minus h cube over 3 factorial f triple prime of x plus h4 over 4 factorial f4 times the prime xi plus minus where xi minus epsilon belong to x minus h and x and xi plus epsilon belong to so xi plus belong to so there is no epsilon, so what this is the sign of belongs to xi minus belongs to this and xi plus belongs to x plus and to x plus h. Hence f of x plus h minus 2 f of x plus f of x minus h over h square is equal to f prime double prime of x plus h square over 4 factorial into f 4 times